Good evening to all of you. This is again Anand Sharma HD, Assistant Professor of Physics, Government First Grade College, Vartur, Bangalore. I am here continuing the second session of BSc Physics, 6th semester paper 8, and the topic is Quantum Mechanics Part 2. In the first session, we discussed about introduction to quantum mechanics, and then uh, major differences between Newtonian mechanics, classical mechanics, and also we introduced the concept called wave function, which is the ultimate for any particular physical system. Now, in this second session, our objectives are to set up Schrodinger's time-dependent equation. There is a fundamental equation associated with the wave function with respect to every physical systems. And such equation is what we call it as the Schrodinger's equation. There are two forms of the Schrodinger's equation: time-dependent equation and a time-independent equation. So in this session, we shall try to understand how to set up Schrodinger's time-dependent equation. About time-independent equation, we shall discuss in the next session. This is what the major objective of this particular session. Now, the second important objective is to know the operator form of momentum. The third one is to know the operator form of energy. So while setting up the Schrodinger's time-dependent equation, we are going to write down operator forms for two important physical quantities, momentum and energy. There is a fundamental postulate of quantum mechanics, which we will be discussing a little later, which says that each and every physical observable in the quantum mechanics can be replaced by an operator. So here right now, while setting up the Schrodinger's time-dependent equation, we are ready to know operator form for two important quantities, momentum and energy. So therefore, another important objective of this particular session is to know the operator form of linear momentum as well as the operator form of energy. And the last objective, of course, we are going to set up the Schrodinger's time-dependent equation in one dimension. I shall try to show how to extend Schrodinger's one-dimensional equation into three-dimension. So therefore, these are the four important objectives of this particular session. We are going to discuss one by one. Now let us try to understand about the Schrodinger's equation. So whenever we discuss Newtonian mechanics, we always mention one particular equation. The particular equation, the fundamental equation, so in Newtonian mechanics is obviously Newton's second law of motion. So that is F is equal to ma in one particular form. So therefore, we can say that Newton's second law of motion is a very fundamental equation of Newtonian mechanics. Similar to Newtonian mechanics, even in quantum mechanics, we have a fundamental equation. And that fundamental equation, in the case of quantum mechanics, is what we call it as Schrodinger's equation. Basically, it is a wave equation for the wave function psi. So therefore, we can say that Schrodinger's equation is a fundamental equation of quantum mechanics. Basically, it is a wave equation. The wave quantity that is associated with the matter waves or the de Broglie waves is wave function that we have discussed already in the previous session. So therefore, a wave equation associated with the variable, so wave function psi for a given physical system is nothing but the Schrodinger equation. So therefore, we need to understand how to set up this Schrodinger equation. So for time dependent cases, this is what the main objective. This is what about the Schrodinger's equation. Now, so the motion of a particle of atomic dimension cannot be described by Newton's second law of motion. So I have already told there is a thing called 100% determinacy in the case of Newtonian mechanics. So this 100% determinacy cannot be applied to phenomena that occur in the case of quantum mechanics, for example, subatomic worlds. We need to make use of uncertainty principle as well. We have already discussed this one. So therefore, if we want to understand the motion of atomic particles, atomic dimension particles, definitely we cannot use a Newton's second law of motion. So in Newton's second law of motion does not give proper answers regarding the motion of a particle of atomic dimension. So therefore, in order to describe motion of subatomic particles, so we need to apply Schrodinger's equation. So therefore, the importance of Schrodinger equation is definitely, so we are going to use this equation in the case of subatomic particles. So basically it is a differential equation which controls the behavior of the wave function psi of the given physical system. So mathematically speaking, Schrodinger equation is a differential equation. So once we solve the equation, we are going to end up with certain solutions, and these solutions actually describe the behavior of the given physical system. So in terms of the wave function psi. So therefore, the process or the mechanism is to set up an equation called Schrodinger's equation for a given system, which involves a differential equation in terms of the psi, and under suitable conditions, we need to solve the wave equation. So, and once we solve the wave equation, we are going to end up with the wave function psi, and this wave function psi actually gives maximum information regarding the behavior of the system. So therefore, we can conclude that Schrodinger's equation is something like a very fundamental equation of quantum mechanics, just like Newton's second law of motion is fundamental to Newtonian mechanics or classical physics. So let us try to set up Schrodinger's time-independent equation. Time-dependent form, Schrodinger's equation, time-dependent equation. In quantum mechanics, the wave function psi corresponds to the wave variable y. If you consider a wave, one-dimensional wave, for example, sound wave, that one-dimensional wave is represented by an equation which involves the displacement of a particle in the sound wave, and the displacement is actually denoted by y. For example, y actually denotes the displacement of a sound wave. So therefore, respectively, the quantity that we are going to choose in the case of quantum mechanics is the wave function psi. So therefore, the wave function psi is analogous to the wave variable y of the ordinary mechanical wave. So, but there are certain differences between this wave variable y in the case of ordinary waves and the wave function psi of the quantum mechanics. So in the case of quantum mechanics, so the wave function psi is actually not a measurable quantity. This we have already discussed in the previous session. Psi by itself directly is not a measurable quantity. So therefore, it doesn't have a physical meaning directly that we have already discussed in the previous session. Not only that one, the wave function psi is a complex number. Since it is a complex number, so therefore it is not a measurable quantity. So therefore, in order to represent a matter wave or a de Broglie wave, so in which the wave function is represented by psi, let us say we are discussing one-dimensional case where the de Broglie wave is traveling along x direction. Then the wave function associated with that moving particle, de Broglie wave of that moving particle which is moving along positive x-axis, is represented by the equation psi is equal to a exponential minus I omega t minus kx, where a is some amplitude of the wave function psi. So, and there are certain quantities inside this particular equation, equation 1. So I is, as usual, it is imaginary number, square root of -1, and that's quantity omega is nothing but your angular frequency, and that angular frequency can be written as omega is equal to 2 pi nu. So where mu is the frequency of the wave, here mu is the frequency of the matter wave or the de Broglie wave associated with a given particle or for a given physical system. And k is, there is another term here, that is k, and k is what we call it as propagation constant. And propagation constant basically is a vector quantity. Anyhow, right now propagation quantity, the magnitude of the propagation constant k can be written as 2 pi by lambda, where lambda is the wavelength of the de Broglie wave. So directly we are borrowing this equation from the classical wave theory. So therefore, just like a classical wave is represented by this equation of this particular kind, so our de Broglie wave associated with a moving particle is also represented by the same type of equation, where omega is angular frequency, so which is given by 2 pi nu, and k is called propagation constant. In terms of wavelength, it is given by 2 pi by lambda. Now, in order to make this equation applicable to quantum mechanics, we need to make certain changes. So in order to make those changes, we are making use of quantum theory. According to quantum theory, E is equal to h nu. Planck's quantum theory says the energy of a quantum is given by h nu, where nu is the frequency. So therefore, frequency nu can be written by energy by h, Planck's constant, E by h. So therefore, once we insert this equation in the angular frequency expression, omega is equal to 2 pi nu, we are going to get omega is equal to 2 pi nu, that is equal to 2 pi E divided by h. And this term h by 2 pi is a very famous quantity, and that is taken as a h cross. So therefore, angular frequency omega can be written as E by h cross, where h cross is h by 2 pi. Planck's constant divided by 2 pi, another important constant, so in quantum mechanics. Now, we are also making use of de Broglie wavelength expression. So using de Broglie wavelength expression, we can write B is equal to h by lambda, or we can also write constant k is given by 2 pi by lambda. Since lambda is equal to h by p, so therefore we can write k is equal to 2 pi h by lambda. So therefore, h by 2 pi is again h cross. So therefore, we can say that the propagation constant k becomes equal to p by h cross. This is equation 3. So what we are going to do now is, so we are going to insert this equation 2 and equation 3. Equation 2 and equation 3. Equation 2 is the equation for angular frequency omega, which is given by E by h cross. And equation 3 is nothing but expression for k, which is given by P by h cross, where E is the energy of the particle now for the given particle, and P is nothing but the linear momentum of the particle, which is traveling along x-axis. Along with there is an associated wave function psi. Now let us use this equation 2 and 3 in equation 1, the original equation. So therefore, we are going to get the solution psi is equal to a exponential minus I omega t minus kx, and that can be written as a is equal to exponential minus omega. So omega now should be replaced by E by h cross. So therefore, we have E by h cross times t minus k is nothing but P by h cross. So therefore, it is P by h cross into x. So 1 by h cross can be taken outside. So therefore, the psi becomes equal to a constant, into exponential minus I by h cross into E into t minus p to x. Now see, this is a one-dimensional case that we are discussing. So therefore, wave function psi is function of the x coordinate and time t. So therefore, the wave function that we have written in the equation 4 is actually written as psi a function of x and t. So this is what equation 4. So which represents the wave function associated with a moving particle in quantum mechanics. Now the rest of the thing is mathematics. We are going to differentiate equation 4 with respect to time. So if we differentiate equation 4 with respect to time, we are going to get dou psi by dou t. I have not done this differentiation completely here, but it is very easy to show that the differentiation dou psi by dou t is equal to minus I E by h cross times psi. So therefore, once we differentiate equation 4 with respect to time, and if we do little simplification, we end up with the equation dou psi by dou t is equal to minus I E divided by h cross times psi, where I is imaginary numbers, square root of minus 1. So this is equation 5. Now we are going to differentiate equation 4 with respect to x twice. Now in the equation 5 we differentiated psi with respect to time once. Now the equation 4 must be differentiated twice with respect to x. And if we do little mathematics, differentiation and simplification, we are going to get another expression dou square psi divided by dou x square. It is because we are differentiating equation 4 twice with respect to s. So therefore, there is a double differentiation. So therefore, dou square psi divided by dou x square is actually equal to minus p square by h cross square times psi. Again, so it is possible to show this simple step using differentiation of equation 4 twice. So therefore, at the speed small compared to with that of light and relativistic limits, we are discussing what we are discussing here is we are trying to set up this Schrodinger's equation in the non-relativistic limit. You all know that a non-relativistic limit is a case where the motion of the particle such that the velocity of the particle is much smaller than the velocity of light in vacuum c. So therefore, considering the non-relativistic case, so the total energy E of a particle is the sum of kinetic energy P square by 2m and its potential energy V. So therefore we can conclude, we can write down expression for the total energy of the moving particle. We are assuming that moving particle is under the influence of a force field, potential field. So therefore, because of the influence of the force field and the potential field, our particle is not only possessing kinetic energy, it is also possessing potential energy. So therefore, expression for kinetic energy is p square by 2m and expression for potential energy, let us write it as V. So therefore, the total energy of the particle E under non-relativistic limit is simply equal to the sum of kinetic energy P square by 2m and potential energy V. And potential energy V in general can be a function of both x and t. Just like wave function psi is a function of x and t, so the potential energy V, the potential energy function V is also a function of x and t. So therefore, we can write total energy of the particle as, so E is equal to P square by 2m plus V. Now this is equation 7. We are going to multiply equation 7 both sides by psi. So if you multiply the equation 7 by psi, the wave function, then we are going to get E psi is equal to P square psi divided by 2m plus V of psi. So this is equation 8. So what we have done is we have multiplied equation 7 on both sides by the wave function psi on the right side. So therefore, we have ended with equation 8, and that equation 8 says that E psi is equal to P square psi divided by 2m plus V of psi. Now we are using equation 6 and 5 in 8. Just I would like to show equation 6 and 5 once again. So equation 5 says that dou psi by dou t is equal to minus IE by h cross times C. And equation 6 is dou square psi divided by dou x square is equal to minus p square by h cross square times psi. So we are inserting equation 5, equation 6 in equation 8, which is nothing but the expression for the total energy. And once we substitute, we end up with this equation. So I h cross dou psi by dou t is equal to minus h cross square divided by 2m dou square psi divided by dou x square plus v of psi. So this is what the equation we have got after substituting the expression for E and expression for P in the equation 8. So therefore, here we are ended up with the equation, differential equation, and the differential equation is such that on the left side we have, so time derivative dou psi by dou t, so times I h cross. So h cross can be treated as a constant right now, but anyhow we have a differentiation of the function psi with respect to time t. On the right side we have, so h cross square minus h cross square by 2m into dou square by psi divided by dou x square. So therefore there is a differentiation of the term psi with respect to x twice. So therefore we have the term dou square psi divided by dou x square. And of course, there is another term because of the potential energy of the particle which is moving in a force field and a potential field. And that force field or the potential field V is also, in general, it can also be a function of so position and time x and t. So therefore, we have another term V times C, V times psi. So this is equation 9, and this equation 9 so is what we call it as time dependent Schrodinger's equation in one dimension. What we have done is we have set up Schrodinger's so equation, so time dependent equation in one dimension. Since we assume that our particle is moving like x-axis, so therefore this is one-dimensional case. This is what one thing. And there is a term dou psi by dou t on the left side. So therefore, so this equation is what we correct as time-dependent Schrodinger's equation. So here the wave function psi is in general is a function of position coordinate x as well as it is a function of so time t also. So therefore we can say that wave function psi here in this particular equation 9 is not a constant, it actually keeps on changing with respect to time t. So therefore the left side I h cross into dou psi by dou t actually gives the time evolution of the wave function psi of the given particle or the given physical system. So that's why this equation is what we correct as a time-dependent Schrodinger equation in one dimension. Now, rest of the thing is very trivial. We can actually generalize time-dependent Schrodinger equation into 3 dimensions. And in order to generalize, it is a well-known fact that we have to include 2 more factors on the right side, the first term of the right side. For example, on the left side we have I h cross divided by dou psi by dou t. On the right side we have h cross by 2m. For one dimension we had only one term dou square psi divided by dou x square. Now if the particle is moving along a 3-dimensional space, so therefore the wave function of the particle is a function of so x comma y comma z coordinates as well as time t also. So therefore since wave function is a function of not only x coordinate, y coordinate and z coordinate also, so therefore we have 2 extra terms. So therefore we have dou square psi divided by dou x square plus dou square psi divided by dou y square plus dou square psi divided by dou z square. So plus of course v of psi, v, so potential function, potential field function, and that potential field function now again is a function of so 4 different coordinates. So those 4 coordinates are x, y, z and t. In some of the cases, the potential function may be a function of only the space coordinates x, y, z. It may be independent of time. But here, while writing the general form of the so Schrodinger's equation, we need to assume that the wave function, potential function, just like the wave function, is also a function of space coordinates x, y, z, as well as time coordinate t. So therefore, so the equation 10, so I h cross dou psi by dou t is equal to minus h cross by 2m into dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus v of psi is nothing but so time dependent form of Schrodinger's equation in 3 dimensions. We can also simplify this equation in a simple manner. We all know that the operator dou square by dou x square plus dou square by dou y square plus dou square by dou z square, it is a mathematical operator. That mathematical operator is what we call it as the famous Laplacian operator in the mathematics. So therefore, instead of writing dou square by dou x square plus dou square by dou y square and dou square by dou z square in detail, we can also replace that one by a Laplacian operator, and that Laplacian operator is written as del square. So therefore, in terms of so the Laplacian operator del square, Schrodinger's equation in 3 dimension time dependent form is now given by I h cross dou psi by dou t is equal to minus h cross square divided by 2m del square psi plus v of psi. So equation 11, and this equation 11 is actually Schrodinger's equation in 3 dimensions, of course time dependent form. So this is what the equation we wanted to set up, and we did it. So therefore I can conclude so that equation 9 represents a time dependent Schrodinger's equation in 1 dimension. And once we are able to write the time dependent equation in 1 dimension, extending it to 3 dimension is very simple. And once we extend, so therefore we end up with 3-dimensional form of the Schrodinger's equation. And the 3-dimensional form of the Schrodinger equation in the terms of Laplacian operator can be written as I h cross dou psi by dou t is equal to minus h cross square divided by 2m del square psi plus v of psi. So therefore equation 11 represents Schrodinger's equation in 3 dimension. So therefore our objective was to set up Schrodinger's equation in 1 dimension and 3 dimensions, and therefore we are successfully able to write those equations. Now I also told one more thing. We wanted to write the operator, we wanted to know the operator form of momentum and energy. So this is clearly evident in the equation 9. So in the place of E, we have written IH cross divided by dou t. So therefore, in quantum mechanics, when energy is an observable, total energy of the particle is an observable. So according to quantum mechanics, one of the postulate of the quantum mechanics, which we are going to discuss little later, each and every observable is represented by an operator. So therefore, that operator is what we call it as the respective operator, physical observable operator. Here, in this case, energy E should be treated as an observable. Of course, energy E is an observable, and this energy observable is replaced by a quantum mechanical operator. The quantum mechanical operator for energy E, as per this equation 9, is given by minus IH cross dou by dou t. So therefore, the quantum mechanical operator form of energy is IH cross dou by dou t. I have not written this one explicitly. I have written in my next session, the third session or the fourth session or so. But anyhow, I would like to say that the operator form of the total energy is IH cross dou by dou t. Similarly, we have another operator p square. So p square is nothing but square of the linear momentum. So the square of the linear momentum operator is actually given by minus h cross squared by 2m into dou square by dou x square. So therefore, we have another important parameter operator. So square of the momentum operator. Square of the momentum operator as per equation 9 is actually given by minus h cross square divided by 2m dou square by dou x square, of course in one dimension. In three dimensions, so the operator form actually becomes minus h cross square by 2m dou square by dou x square plus dou square by dou y square plus dou square by dou z square. I'm going to mention all these operators little later in my next session or the next one also. So therefore, our objective is fulfilled now. We wanted to set up Schrodinger time-dependent equation. We wanted to extend it for 3 dimensions, and we did it. And we did it just by making use of the classical wave equation. Using the classical wave equation and by doing certain modifications as per de Broglie wavelength expression and Planck's quantum theory, we are able to set up Schrodinger's time-dependent equation in one dimension as well as 3 dimension. And also, so I told, so physical observables are operators in quantum mechanics. So therefore, there are two physical important operators or parameters in physics. So momentum and energy. So this momentum and energy observables, they actually take an operator form in the quantum mechanics, and we are also able to write down the operator form for the momentum and the energy. So this is about Schrodinger's time-dependent equation. There is another form, that is what we call it as Schrodinger's time-independent equation, that we are going to discuss in the next session. So I am going to end up this session. Thank you, one and all.